A very good day to everyone. So we proceed with the next chapter, which is phase equilibrium. Okay, first of all, what is meant by phase? Because we still remember, if you want to recall, we have learned on the phase diagram during the first chapter. So of course, what is a phase? A phase is a part of a system uniform throughout in chemical composition and physical properties that is separated, a uniform component part of the system that is separated from the other homogeneous part. For example, we can have solid, liquid, or gas by point resurfaced. A phase may of course contain several chemical constituents which may or may not be shared with other phases, and the number of phases is represented by the relation by P, which is P phase. For example, if you have some ice floating in water, you have a solid phase present and a liquid phase. If there is a air above the mixture, then there is another phase. So that is meant by phase, alright? Okay, the next one is the degrees of freedom, which is F, is the number of independent intensive variables, which is those that are independent of the quantity of material present that need to be specified in value to fully determine the state of the system. Typical such variables might be temperature, pressure, or concentration. Okay, we move on to the Clapeyron equations. I believe we have learned this during chapter 3 or 4, right? Okay, so consider one component system with two phases, alpha and beta. At equilibrium, T, P, and mu are the same in the two phases. When T only changes or P only changes, one of the phases will disappear. However, when both T and P change in such a way to keep mu is equal, in the two phases will continue to coexist. So this is the coexistence curve for the system of alpha beta, and whereby we can see along the curve, mu a alpha equals to mu b beta. Sorry, if t changes by dt, then p will change by dp. At point one, where we can have alpha one alpha. Sorry, mu 1 alpha equals to mu 1 beta. At point 2, mu 1 alpha plus d mu alpha equals to as follows here. Okay, so we can make a conclusion, or we can make assumption. We can make the conclusion that d mu alpha equals to d mu beta, since d mu equals to dgm equals to v dp minus s dt. Thus, we can have v dp minus s dt equals to v beta dp minus s beta dt. So it is parallel. So this equation, especially this one, dp, can be applied to vaporization, sublimation, fusion, or transition between two phases. So this is to describe the T and P of the two phases. Okay, next one. Heat of vaporization of water 40.69 kilojoule per mole. And given this value, what is the change in the volume boiling points of water per Pascal? So we can use the previous equation. So we have all the data given here, and then we can get the dt per dp, which is the boiling point per Pascal, right? Remember. So make sure that unit is very important. And next one is calculate the change in the pressure required to change the freezing point of water. At the degree C, the heat of fusion of ice is given, and the density of water is given there, and ice is given. So we have here also the same equation. So we can get Pascal over Kelvin, and we can just change the unit into bar over Kelvin. Good. So this is example of transition of the phase. Okay, the Clausius-Clapeyron equation. Clausius modified Clapeyron equation by neglecting the molar volume of liquid in comparison with molar volume of the gas. Okay, so this is the equation previously, and we can have this one, and then we rearrange it into this one, and then we can get these equations. And by plotting this one ln against 1 over t, delta H can be calculated for vaporization or sublimation. Also by limits the integration, so we can have here, whereby by using another graph or another plots, so you can have these equations. And however, the effects of this equation to represent a p as a function of t over a wide range of t is necessary to consider as t dependence, and whereby the vapor has to be assumed to be in the ideal condition, whereby ideal gas. Okay, next one is Trutten's rules. The molar entropy of vaporization at the standard boiling point, the boiling point at 1 bar, is a constant, and its value is about 88.7, joule per Kelvin mole. So we can have here delta S equals to the 88 joule per Kelvin mole. By using the rule, delta H of liquid can be estimated approximately. So we can have delta S vaporization equals to H vaporization per T boiling point, TB. An example, the boiling point of benzene is 80.1 at 1 atmosphere. Estimate the vapor pressure at 25 degrees C using Chilton's rule. So the vapor pressure is given here, so we have to convert it into the appropriate unit, and then according to the rules, according to the Chilton rule, so we have delta S and delta T here. So we can get this equation by using the ln the correlation between this one and this one, HGB and L P2. Okay, this one P2, and right, use this one, so you can get the bar or the pressure, the vapor pressure at 25 degrees C using the rules. Okay, next one is vapor liquid equilibrium of binary liquids mixture. When a binary liquid mixture is in equilibrium with its vapor at constant temperature, so we have the equation, this one, whereby the chemical potential of each component is the same in the gas and liquid phase. And assuming that the vapor is in either gas, so we have this one as assumptions. And for the liquid mixture is as follows, whereby A is in the activity, so we have to convert it into this one. So we can get for a pure liquid is activity equal unity. So we can have another equation whereby the P is the vapor pressure of the pure liquid. By subtract the last equation for pure liquid from that in a mixture, so we have another equation whereby this one can be used for ideal behavior of the vapor. Okay, next one is Raoult's law. For a certain solution which is ideal, the partial pressure of a component is equal to the mole fraction of that component times the vapor pressure of the pure component, P equals to XP. This law is correct where the components are quite similar, since the gas phase assumed to be an ideal gas, so we have P equals to YP, which is Dalton's law, where Y is the mole fraction of I in the gas phase and P is the total pressure. As shown in the figure, change of vapor pressure for benzene toluene mixture also with vapor pressure of both benzene and toluene solution against the composition of solution, and the behavior of this mixture follows the ideal solution behavior and of course the Raoult's law. And for this solution, it is possible to calculate the composition of its vapor which in equilibrium with the solution. So we can see here that it is in equilibrium between benzene and toluene. Okay, for a mixture of two liquid, 1 and 2, so we have Y equals to P1 per P and Y2 equals to P2 per P. From the Raoult's law, we have to substitute it into XP per P equals to Y2 equals to X2 P2 per P. The relative mole fraction of components in the vapor pressure, thus we have Y1 over Y2, so we have to change and rearrange everything. And from this diagram, at any specific vapor pressure, it can be determined, and the corresponding composition of liquid mixture, or at any specific composition of liquid mixture which can be determined the corresponding composition in vapor pressure. So we can see from the line, from the figure given here, the liquid composition line and the vapor composition line along the bubble line. and also the dew line. Okay, next one. Okay, we have one example at 60 degrees C. The vapor pressure of pure benzene and toluene are 0.513 and 0.185 bar respectively for a solution with zero point 0.6 mole fraction toluene. What are the pressure of component? What is the mole fraction of toluene in the vapor? So we have here a pressure 1 and 2, and we don't have Y2, and we have what is P2. So we have from the variation of Rock's law just now, xp, y, we substitute to xp. So after several rearrangements, so we have y2 equals to p2 per p total, so we have 0.351. That is the partial pressure. Sorry, that is the mole fraction. So this is the partial pressure. Sorry, this is the partial pressure of the components P1 and P2, and we have P total, and then this is the mole fraction of toluene. Okay, so you can refer to this next example. All right, I'm not gonna read through, and then you can refer to it. How we can also relate to the equation given just now, so we can have this correlation, whereby we can get the vapor composition and total pressure for solution. This is very important, yeah, because this will be included in the final exam. So how you want to determine the composition for each liquid and gas. Okay, next one is non-ideal mixture of liquids, the deviation from the Rock's law. By plotting the vapor pressure of an ideal mixture of two liquids against their composition, you get a straight line graph like this. In this case, pure A has the higher vapor pressure and is the more volatile component. Okay, so we can have this several graph, which is the deviation from the Rock's law. So basically, it is the different parameters, and in this case we can see that pure A has the higher vapor pressure, and so is the more volatile component. Okay, next one is a positive deviation from Rock's law. In mixtures showing a positive deviation from Rock's law, the vapor pressure of the mixture is always higher than you would expect from ideal mixture, and hence have lower BP. Because the vapor pressure is higher, the liquid is evaporating more easily than would be expected. This means that some of the intermolecular bonds in the liquid must have been broken when the liquids were mixed. Example, it means that the molecules are breaking away more easily than they do in the figure pure liquids, because the intermolecular forces between the molecules of A and B are less, and they are in the pure liquids. So again, this is the phase behavior. And for example, right, the mixture of ethanol and water. The ethanol molecules have an average of 100 hydrogen bonds per molecule, whereas the water molecules have two. The ethanol molecules interfere with the hydrogen bonds and therefore make the liquid more volatile. In the meantime, for ethanol and benzene, the hydrogen bonding in the ethanol is reduced by the presence of the benzene. Okay, this is okay. Meantime, for the negative deviation from Rock's law, so look at the curve. The curve for the positive is 1, and for the negative it's going downward. In exactly the same way, having mixture with vapor pressure which are less than would be expected by Rock's law, and these are cases where the molecules break away from the mixture less easily than they do from the pure liquids. New, stronger forces must exist in the mixture than in the original liquids. For example, the intermolecular forces increase when the liquids are mixed. This is generally because molecules where no hydrogen bonding is present are mixed to form a liquid with hydrogen bonds. For example, right, we have trichlorometane and C18 and says Cl3 has a polar hydrogen atom but no lone pairs and therefore cannot form hydrogen bonds, which is as listed down here. Has lone pairs on the oxygen but no polar hydrogen atom and therefore cannot form hydrogen bonds. When mixed, hydrogen bonds form, decreasing the vapor pressure. Sorry, my mistake actually. Okay. Next one is boiling point, which is the composition diagrams. The boiling point of liquid mixture is the temperature at which the total pressure of liquid mixture equal to the atmospheric pressure, whereby at constant temperature the VP, the pressure of liquid mixture, is changed with the composition of liquid, as it was shown before, and also at constant pressure at 1 atmosphere, the boiling point of liquid mixture is changed with liquid composition. In the meantime, for the ideal mixture, the vapor composition line is over the liquid composition line, whereby more volatile component has high content in the vapor here in the vapor line, right? Okay, we take example the toluene benzene mixture. The point on the lower curve at the molar fraction or the mole fraction of benzene of about 0.33 here. Of benzene, this point gives the boiling point of a mixture which is 0.33 mole percent benzene. Okay, so this is benzene. Sorry, this benzene. Mm. Which is what is the composition of the vapor which is in equilibrium with the liquid at this temperature. So the vapor composition must lie on the horizontal, whereby constant temperature line going through this point, right? At any given temperature and pressure, the composition of the vapor must be richer in the more volatile component, and benzene is the more volatile component. And this line is a tie line, and it intersects the upper curve at the composition of the vapor in equilibrium with the liquid at the same temperature. That is the same temperature here. So this is the point of the tie line. And the region between the two curves is the two-phase region. In this region, two phases, liquid and phase gas, are in equilibrium with each other. Okay, if we hit a liquid mixture at a composition of about 0.33 mole fraction benzene, the liquid will have the composition shown at point A, so here, when liquid first begins to boil. The first vapor to come off will have the composition shown at point B. So after that, as we continue to heat the system, the more volatile component will evaporate preferentially and the liquid phase will become richer in the less volatile component, which is toluene here. As we continue to heat the mixture, the toluene will gradually catch up to the benzene in the vapor phase. The very last bit of liquid to evaporate will have the composition shown at point C here, and the vapor will have the original composition that we started with D or A, as you suggest. And notice that as we heat the system, the tie line tracks with the lower and upper curve to give the composition of liquid and vapor in the equilibrium. Okay, next one is fractional distillation. So boiling diagrams provide an explanation for fractional distillation. Suppose we start with the liquid mixture with 0.33 mole fraction benzene. As we heat the liquid, it will begin to boil. When the temperature reaches the temperature of point A, the first vapor to come off has the composition shown at point B. Capture the vapor, condense it, and heat it up. The new liquid will boil at point C, giving a vapor with composition at point D. Capture this vapor, collate, and boil it at point A, and so on. By continuing this process, the vapor can be made as pure in benzene as we always desired. And this is what fractional distillation does. There are more modern ways to separate mixture, for example chromatography, but fractional distillation still has industrial and some laboratory significance. Okay, boiling diagrams from for non-ideal solution. As we was explained earlier, the solution with positive deviation from Rod's law has a higher vapor pressure that would be given by Rod's law. That means that the solution will boil at a lower temperature than would be expected from Rod's law, and the boiling diagram for such a substance might look like the following, whereby point A denotes a constant boiling mixture called an azeotrope or low boiling azeotrope. When a system is azeotrope, its component cannot be separated by simple fractional distillation. Really important. Okay, in a mixture with negative deviation from Rod's law, the vapor pressure is lower than would be expected from Rod's law, which will produce boiling points higher than expected and a high boiling isotope. When a system is in azeotrope, its component cannot be separated by simple fractional distillation. So the behavior is also uh, different for this situation. And cooling curve for pure substance. So basically, if you still can remember, we uh, we are revising the same thing. I'm like what we have learned in the phase diagram figure. Okay, if there is a pure molten lead and it was allowed to cool down until it has all solidified. Plotting the temperature of the lead against time will give a typical cooling curve for a pure substance, which is this one is the typical one. Throughout the whole experiment, heat being lost to surroundings and yet the temperature doesn't fall at all while the lead is freezing. This is because the freezing process deliberates heat at exactly the same rate that is being lost to surroundings, whereby in this case energy is released when new bonds form. In this case also the strong metallic bonds in the solid lead lat in specific. Okay, for example, we have this thin lead mixture. This is the figure, the cooling curve. Okay, what is interesting is eutectic mixture. So this particular mixture is known as a eutectic mixture. The word eutectic comes from Greek and means easily melted. So in this one, in this case, it is easily melted at certain temperature. And the eutectic mixture has the lowest melting point, which is of course the same as the freezing point of any mixture of lead and tin. And the temperature at which the eutectic mixture freezes or melts is known as the eutectic temperature. Okay, next one is the phase diagram. Start from the data obtained from the cooling curve. Draw a graph of the mixture at which freezing first starts against the proportion of tin and lead in the mixture. The only unusual thing is that you draw a temperature scale at each end of the diagram instead of only the left hand side. Okay, so this is the graph of the figure is all about. So it is molten tin and lead. So we have here the behavior of solid lead and solid tin according to different composition. So this one is we are starting with the mixture here on the phase diagram, and next one we have here. Lead starts to freeze when the temperature fails to here. Uh, and next one is the temperature and composition of the liquid move along this line as far as the eutectic point. Okay, so here we can have the eutectic point. When it has reached the eutectic point, if the temperature continues to fall, you obviously just move into the region of a mixture of solid lead and solid tin. In other words, all the remaining liquid freezed. So I believe this can be applied for freeze drying or another freezing applications. Okay, we have tin lead mixture as a solder. Traditionally, tin lead mixture have been used as a solder, but these are being phased out because of health concern over the lead. This is especially the case whereby the solder is used to join water pipe where the water is used for drinking. New lead solder have been developed for as safer replacements. Okay, for this one, so I think this is religious history. So okay, for the two components system whereby solid and liquid phase, in this system, the components are completely miscible in liquid phase and immiscible in the solid phase, so that the pure solid phase separate out in the cooling. And for this cooling curve, whereby we have temperature of the time at constant pressure for the system bismuth cadmium, when the molten solution of bismuth or cadmium is cooled, the plot has nearly constant slope. So here, constant, and when the solid crystallize out, the plot becomes horizontal result from a heat evolution like a 27.3 and 323 for bismuth and cadmium, sorry, respectively. When the solution is cooled, there is a change in the slope of the cooling curve at the temperature at which one of the components begin to crystalline out. Such change in slope are evident in the cooling curve of 20% of cadmium and 80% of cadmium. All the cooling curve, all solutions show a horizontal section at 140 degrees C. At this temperature, both bismuth crystallize out. This is an eutectic temperature. The eutectic is not a phase, it is a mixture of two solid phases and has a fine grained structure. Okay, basically, more about eutectic point. So we can see here the temperature composition diagram of bismuth cadmium. In the area above JKL, you can hear JKL, and the area above it, there is one phase whereby we have freedom equals to 2 minus phase plus 1 at constant pressure. So we have for F equals to 3 minus P at constant pressure for a single phase. So P is 1 and this one F2 degree of freedom is 2. 2 degree of freedom is unnecessary temperature and mole fraction to define any point in this area. And along JK, which is here, um, bismuth freeze out. Along LK, cadmium LK here, CD cadmium freeze out. There are two phases, solid and solution, having a composition given by the line JK and LK respectively. So we have here, but the degree of freedom is 1. Only temperature of composition, which is the mole fraction of liquid, can be specified. At the eutectic point K, there are three phases: solid, bismuth, solid, cadmium, and liquid solution with 40% cadmium. So we have here, if we calculate the degree of freedom and the phase, so we have 0. So 0 degree of freedom, there is only one temperature, only one composition, at which the three phases coexist at a given constant pressure of liquid can be specified. It represents the lowest freezing point of whole solution series, and the eutectic mixture is a mechanical mixture and not a compound, right? Remember that. And the area below the eutectic temperature K is a two-phase area whereby solid bismuth and solid cadmium. So again, for this another situation, another scenario is we have we calculate the degree of freedom and the phase. So we have the degree of freedom as 1. Only one temperature is needed to be specified, whereby composition may not be necessary because both bismuth and cadmium are present in pure components, and the addition of cadmium lowers the freezing point of bismuth along JK, and the addition of bismuth lowers the boiling point of cadmium along LK. Or JK is the solubility curve for bismuth in liquid cadmium, and LK is the solubility curve for cadmium in liquid bismuth. Okay, calculation of the solubility. Whereby to determine the molar mass of a solute B in a solvent A by the depression of the freezing point of A, assume the solution is ideal and that pure crystalline A freeze out of solution. An equation for the equilibrium is given here. Thus, at T temperature at which two phases are equilibrium, so we can just substitute it. And this one is the Gibbs energy of fusion of the solute at T. So we have another equation, and substituting this equation in the above one, so we have ln xa equals to blah blah blah, and it follows this equation. Okay. Okay, next one is we will have a question. Okay, calculate the solubility of an ideal solution at 150 and 200 degrees C. If the H equals to 10.5 kilojoule per mole at 273 and T equals to 273. Okay, I'm not going to show you and of course you have to use this equation. Oh, sorry. Okay, I'm not going to show you the answer. So basically, you just have to follow this equation. All right. Give your answer in the comment section down below, and we will proceed with the next section. Thank you.